Okay, so let us start. If I don't feel well, I'll end the class early. So for now, I'm fine. So I'm hoping for a full class, but let's see. Okay. So in the last lecture, if you remember, we kind of wrapped up our discussion on gradient descent. We talked about initialization. We talked about batch normalization, and we ended the lecture with a table, right? What are the different challenges that you face, how to diagnose it, and how to solve those, right? For example, local optima. How to diagnose, you don't know. How to solve, you don't know. You just do some few random restart. For example, the other one was uh, ill conditioning. Ill conditioning, batch normalization is one of the idea. How do you know? Well, it is hard, but you can look at the input outputs after each hidden layer, and that will probably give you some idea, right? So today we are going to wrap up our discussion on optimization in deep learning. So fundamentally, we have only talked about stochastic gradient descent till now. We'll talk about in today's lecture about some of the modern and advanced optimization algorithms that are used in deep learning, and that is how we'll wrap up our discussion on optimization algorithms used for training. And then we will start discussing about generalization in deep learning, because the objective is not to just minimize your loss function. The objective is that your model or the model that you are learning should perform well for unseen data, for a new data. And that is what generalization is, and we'll start talking about that as well. So that is more or less the plan for today. So let us start, right? So lecture 9, right? So till now we have talked about variants of gradient descent, I will say. Variants of gradient descent along with their challenges and remedies, right? Along with challenges and remedies, right? Till now we have talked about this thing. So today let us start talking about how we can improve upon gradient descent itself, right? So if you remember, so in gradient descent, what is the update rule? Theta t plus 1 is equal to theta t minus learning rate times the gradient of the loss with respect to the parameters theta evaluated at the previous time step. Sorry, the update rule is theta t plus 1 is equal to theta t minus eta gradient with respect to theta L theta t, right? This is the gradient descent, right? Be it mini batch gradient descent, be it stochastic gradient descent, be it batch gradient descent, this is what is used, right? And the name is justified because you are descending in the direction of the gradient. Now, how can you potentially improve it? Do you have some ideas what we can do to improve it? We will still be in the gradient descent, but how we can improve gradient descent? Any ideas? Looking at this expression, what do you think can we potentially do?
You can change the step size.
Change the step size. Can you elaborate? Change the step size.
Iteration, you can change the step size.
Okay, so you are saying that this eta term need not be constant. Okay, fair enough. Anything else? How will you decide?
So as the number of iterations increases,
Mhm.
we'll be get closer to the optima. Then we can take smaller and smaller.
Okay.
Size.
Okay, fair point. So you can work with the step size, the learning rate, and as you reach closer to the uh, optima, you can probably reduce it. The question is that how do you know you are closer to the optima for different problems? For some problem, you might reach close in 50 steps, 50 epoch, let's say. In some cases, you will probably reach close in 100 epochs. And in some cases, you might reach closer in 150 epochs, right? So how will you decide that? But if we can decide that, that is one of the things we can do. Anything else? Any other idea in which you think we can improve this? Think about the ill conditioning problem last time. So maybe that will give you one of the solution. You remember the ill conditioning problem, what was happening there? When the problem was ill conditions, x1 was too large, x2 was too small. So what was happening to the contour? It was, I mean, slender, I can say, right? In one direction, it was quite, the variation was quite large, other direction, it was quite small, right? Now, in that case, can you think of something? How was the convergence happening there? You remember the diagram I did you last time? How was the convergence? Something like this, right? And why was it happening? Because the gradient was more in the W2 direction, let's say, in the Y direction, whereas the optima was more in the X direction. And it was happening because in this gradient descent formula, eta is a constant. When I say constant, I mean in different direction you do not use different learning rate. So one of the solution is that you will use you will reduce the learning rate as you go over the epochs. The other one is that maybe in different directions you use different learning rate. Why should it be the same learning rate, right? In all the directions. That is the second thing that can happen. Anything else? Anything else is coming to your mind? If you look into this, is I mean, is do you think information of history is important? Information of history, do you think it is important? For example, if it is going like this, that means at each step the direction is changing, correct? With that history information, if I had that history information, I can probably reduce the step size so that it do not go like this, it will go maybe like this. Whereas if it is going like this, from that history I know it is going in the correct direction, so maybe I should take larger steps. The third thing that is possible is somehow we need to bring the uh, information about the history of the updates into picture. Okay, so basically instead of grad of L, there should be something that is talking about also the history. Grad should be there, but something about the history should be there, right? So there are 3-4 things that we discuss, right? Let me write it down. So we can improve gradient descent. And by the way, I'm showing it for gradient descent, but the same thing will hold for stochastic gradient descent, mini batch gradient descent everywhere. I'm just writing gradient descent because it doesn't matter actually. Okay. We can improve gradient descent by, so the first thing was y eta should be constant, right? That was the first point that was raised. So eta should need not be constant. Somehow eta should be able to change not only in direction but also at epoch, right? The second thing is that uh, y eta should be constant, that is one, and the second one is that history information can potentially help. Okay. So which means if I look into this expression, there are two categories that are emerging. One category of algorithms that will work with this eta parameter, the learning rate parameter, that is one category. And then a second category that will work on bringing historical information instead of just the previous gradient update, right? So these are two broader categories that are coming into picture, and then there is a third category also, that why shouldn't we do both? Okay. So if I have to make a table, so we are talking about what? Historical information, right? And then the other one is learning rate. Okay. Now, if you look into historical information, there are two popular algorithms that brings historical information into picture. The first one is momentum. You bring the idea of momentum into picture, so momentum based gradient descent. So the first one is momentum based gradient descent. The second one is Nestrov gradient descent, and we'll talk about both of these algorithms today. Okay. Similarly, if I go to the learning rate part, uh, in that case, in the learning rate part, there is this idea of um, ADAGRAD, which is basically adaptive gradient. So basically, you bring, so you basically work with the learning rate somehow to make it adaptive, how much steps you should take. And then there is this idea of RMS prop, which is an improvement over ADAGRAD. And then lastly, there is this algorithm ADAM, which is the most popular one, which actually combines RMS prop with momentum based gradient. So this ADAM combines RMS prop with momentum based gradient descent. So basically, it is kind of best of both worlds. It is also working with the historical information. It is also updating the learning rate, and this is the state of the art. There are some improvements over Adam that also exist. For example, Adam W. For example, Yogi is one algorithm that helps. So there are those, but somehow Adam I will say is still the state of the art. Okay. Okay. So let us now start talking about one algorithm at a time and see what. Yeah.
Sir, all of these methods are like deterministic. Are there also gradient methods which are stochastic? Like if it's there, you should go in this direction.
I mean, what do you mean by stochastic? That first we should be clear. Stochastic gradient descent, right? Will you call it stochastic or deterministic? First of all.
Like some fraction of the times you don't go where your
Correct.
loss is.
No, it does not exist, or you don't do that. The reason is what you are talking about is basically balancing exploration and exploitation in some sense, which is good by the way, but you don't do it here because given the amount of parameters you are dealing with, you always or most of the time you take a grid each step, which is exploitation, instead of going the exploration route. So exploration is almost never uh, uh,
But we do something like cases for check that again if it is too big then you are just bouncing across the.
correct. So in that case, you work with eta and come up with a better solution of eta, maybe reduce the value of eta, but you don't add a random part. Because if you add a random part, because then it's random, and when it is a million dimensional space, then the chances you will take the correct step, that probability is 10 to the minus 8 maybe. So it is not worth it from the law of probability itself, because there is only one correct path, right? If we talk about global, everything else is wrong. Now consider them to be independent, equally likely, and then do the product, you will find come up with a number like 10 to the minus 8, minus 7. So it, in general, so that's why you don't see exploration in this case. Because you see exploration, for example, in RL, because there the action space is not that big. So that's why in RL you see this exploration business, because there the action space is discrete or continuous, but it is not that big. Okay. Okay. So now let us start with momentum based gradient descent. Momentum based gradient descent, right? And the idea is that you need to bring information about the momentum into picture. This is what you do. I'm just going to write the update rule and then we'll discuss what it actually means. Okay. So P t plus 1 is equal to mu Pt plus eta times gradient with respect to theta L theta t. P is your momentum. Okay, you have to initialize the momentum at some value and then it will run. And then your theta t plus 1 is equal to theta t minus p t plus 1. Okay. So this is the momentum based gradient descent. And now let us try to understand what is happening. What is P? P is your momentum. Okay. And even if you start with a zero momentum, it will have gradient information from the previous steps. It's a recursive formula. So it will have gradient update information from the previous steps. Agreed? Now what will happen if two consecutive gradient updates are in the same direction? What will happen in that case? Two consecutive gradient updates are in the same direction or similar kind of direction. P will take a larger value, right? Which means theta will take a larger step, which makes sense. Historically, if all the updates are in the same direction, you should take a larger step, right? That is what it is ensuring. And what happens if the gradient keeps on changing direction, then P will become small because of the opposite sign, in which case theta will be taking a smaller update. So basically based on the history, the momentum, you are able to decide, in this case, this algorithm is able to decide whether to take larger step or smaller step. Make sense? Any question? Okay. So what it will do is as follow. In if the gradient is too high or not well posed or whatever, right? In that case, it will reduce the step size. Whereas if the gradient is quite well defined and it's always convex kind of function, whatever, in that case, it will increase the step size. So the momentum term helps you deciding the step size based on the history. When multiple steps are taken in the same direction, because of the momentum, this update step increases. When the updates are taking place in opposite direction, in that case, the step is reduced. Well, when did I say eta will change? Step size is not, step size means update size. Eta in deep learning is learning rate. Step size is a deep optimization term. Okay. So that's update, right? Theta t plus 1 to theta t, theta t to theta t plus 1, that updates, right? So if I have to draw, it will be something like this. So let's say, I don't know, but so let's say I start from here and it was going like this. Okay, in that case, with this thing, this oscillation will reduce and it will go like this. Okay, and if the direction was same, then it will converge much faster. Do you see any potential issue with this one? Yes. So near the optima, it can overshoot in both the directions because it is aggressively doing it. So although it will go very smoothly towards the optima, near the optima, it might start going here and there. Okay, because there is no information about the future, it's only the past. Okay. So this helps in deciding this helps in deciding the update step. I mean larger update versus smaller update. Smaller based on you decide based on momentum, and momentum in this case means history, by the way. Okay, this is what it is doing. The challenge, however, is that near the optima, it might fluctuate.
Sir, but once it reaches near the optimum, suppose it overshoot once. So at that point, PT plus 1 and PT will be in opposite directions. So as compared to the vanilla gradient descent, it should like
Correct.
go.
Correct. Compared to vanilla, it is better, but still it should have converged much faster. That's the point. Compared to vanilla, it is any day better. So what will happen? You are right. It will overshoot, and then the shooting will reduce, and it will converge like this. But still, this part you don't want, right? So in that sense. It fluctuates near optima. Okay. It's a vector summation. See, I have not drawn it, but each of this p and all of those things are vector. So if I write the p update, this one, right? This is something like, let's say, pt, mu times pt is something like this. Gradient, and this is this, and your update step is this. So it's a vector, proper vector summation we are doing. So it has direction, it has components, vector components. Okay. Yeah. No, but the question is how much of mu you should take. Empirical value is between 0.9 and 1. I mean, it should not be 1, less than 1. So people take 0.9, 0.95, 0.99, so something like that. It's basically how much of the previous information you will dampen out. That's what it means, right? So it fluctuates near the optima, and to address this, Nestrov based gradient descent was proposed. Nestrov gradient descent addresses this issue. Nestrov gradient descent does one thing. It just does not decide based on the past. It also tries to find out what the next step is going to be and decides based on that. So basically, it has the concept of look ahead. So it first finds a look ahead theta, and then all the updates are based on that look ahead theta. Why is it important? When you look ahead, you can see if you're very near to the optimum, so that fluctuation that was happening near the optimum will reduce. That is basically the idea. So let me again write down the update rule and then we will see. So in this case, it is what? Theta LA is equal to theta T minus PT. Theta LA is the look ahead point. Okay. So you can see that it is PT is what? I mean, it's the exact same thing, right? I mean, minus or plus, yeah, minus, right? It's the same thing. So I'm just using PT instead of PT plus 1. So it's like a approximate look ahead point. And then it remains same. So PT plus 1 PT plus 1 is equal to PT, I mean mu times PT, right? Plus your learning rate times gradient of the loss with respect to theta, and here it changes, it is evaluated at theta LA. So basically your gradient is now evaluated at the look ahead point, and that helps you arrest that fluctuation near the optima to a certain extent. I will not say it is perfect, but to a certain extent it does that, because you are now evaluating at a point which is coming next. So as a result, that fluctuation is reduced. The last step remains the same, which is theta T plus 1 is equal to theta T minus P T plus 1. Okay. So one additional step, so additional computing obviously, but much more stability, at least near the optima. Okay. Clear how the two things are different? They are very similar, just one additional step is coming, otherwise these two are quite similar. In fact, one is motivated from the other. I mean, Nestrov is motivated from the momentum and its limitation. No, 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 no. No. You are so look at this gradient of theta L, theta LA. Now at the look ahead point, if you are near the optima, what will be that term? Gradient of theta LA. At the optima, that term is 0, right? Gradient is 0. So if that is 0, it will not update. So you are not taking a decision. The decision is taken by the fact that you are now evaluating at the next step, right? I mean, it's not exactly same, but it has some similarity with implicit and explicit scheme. I mean, that you use in time integration. I mean, if you know implicit and explicit scheme, I mean, it has some similarity with that. It's not exactly same, but you can draw comparison with that in a certain way. In explicit, what happens is always based on the previous step. Implicit is based on the current step, and that's why implicit is unconditionally stable, right? But you need to have additional computation. Explicit, you need to use very smaller steps. So there is some similarity with that, not exactly same again, right? Okay. So this is your historical information based, right? Now let us go to the other set, which is the learning rate based. Okay. And there the first one we will do is add a grad. adagrad, which stands for adaptive gradient. Okay, and in this case we will play with the learning rate. Okay, again we will follow the same thing. I will write down the steps and then we'll discuss if those steps are making any sense or not. Okay, so in this case the idea is simple. It is not necessary that in each of the theta direction the learning rate should be same. The learning rate should be function of the gradient. I mean, if you remember the yield conditioning one, you remember the learning rate should have been less in this direction and more in this direction. So, and that how do we know that? Because by looking at the gradient. So, some kind of scaling needs to be done with respect to the gradient. I mean, gradients should tell also how much you should move in a given direction in some sense, right? So here what you do is you first compute the gradient g t is equal to gradient with respect to theta L theta t square. Okay. Now here's the catch. What is gradient of loss? Loss is a scalar. Gradient of loss is a vector. What does square of a vector means? It does not mean anything. This is element y square. So if you have, let's say the numbers are 1, 2, 3, it will become 1 square, 2 square, 3 square. So this square is element wise. So each element in your gradient vector is squared. So keep that in mind, okay? Because you need to keep in mind that this is a vector. This is not a scalar. So what does it even mean to do that, right? So this is element wise, okay? Element y square, okay? So you compute your gradient and then one is equal to ST plus GT. Okay. Okay. I mean, you can add a mu also along with ST, but that's fine. I'm not writing it. So basically, and then finally, theta t plus 1 is equal to theta t minus eta divided by square root of s t plus 1 plus epsilon gt. Gt square, right? Square root, I think. Square root of gt. See what have I done? If your s t plus 1 plus epsilon turns out to be 1, then you end up getting your usual gradient descent, right? Again, st plus 1, remember it's a vector. So basically what is st plus 1 doing here? It is deciding, and st1 has the t plus 1 has the information of the gradient. So it is deciding, it is scaling your learning rate based on the gradient in each direction. The direction in which gradient is more, the learning rate will be less. And the direction in which the gradient is less, the step length will be not step length, the learning rate will be scaled to so that it is little bit more. What is the parameter epsilon doing here? 0. So you don't want to divide by 0. So generally, if epsilon value is taken to be 10 to the minus 6, 7, 8, In books, you will also find that epsilon is outside the bracket, sorry, square root doesn't really matter. Okay.
So this square root of GT is also element wise.
Yeah.
And this square root, it should be a scalar. So is this L2 now?
No, it is not scalar. It is element wise. Because what you are doing is that you are saying each theta will have a different learning rate. So it's not element wise. Sorry, it's not scalar.
It is square under like the
Yeah, it's element wise. So it's element wise. So theta t plus 1, right? So theta t plus 1 I is equal to theta ti minus eta by s t plus 1 I, something like that. Okay. So basically each direction now have a different learning rate.
What is the need of doing the square in this whole concept?
It should depend on the magnitude and not the direction. Your scaling should not depend on your. Otherwise, descent will become ascent. You will not realize. So that's why to ensure that descent is descent and not ascent, that square and square root is done. So basically, it's the magnitude that matters, not the direction.
This will also the thing like when the gradient is high, it will based on that it will scale.
When the gradient is high, in eta by gradient will become small. So it will take smaller steps. So generally, gradient is high when. So remember that diagram, right? So gradient was high in this direction. So it will take less step in this direction, more in this direction. The yield condition problem, you remember? So in that sense, right? So instead of, so if I have to draw the diagram, so this was the diagram, right? Something like this. So usually what will happen? Usually it will start from here and then move like this, right? What it will do is that it will make movement in the vertical direction less and horizontal direction more. So as a result, maybe this will move. I should use this. This is what will happen. So the direction movement in this direction has increased, this direction has reduced. So you are actually going in the direction of the optimum. So yield conditioning is also addressed by ADA-grad. Okay.
Will always mean that entries are positive.
No, square root is fine. Yes.
No, the last term.
Yes.
That will mean like all the vector elements are positive.
No, it will. Okay. Okay. There are two things, right? The first one so basically square root of GT should give you the original grad theta L theta term, not the positive ones. Original grad theta L, grad of L theta. You don't, I mean, if you make all positive, then you are letting go of the direction. That's wrong. Okay. So this is basically. Give me 1 second. Let me write this and then I could not listen actually. So this is grad of theta L theta T. Yeah, tell.
Because we said that given that includes only like the direction and then we combine it to build up data. But isn't S of T plus something essentially
Yeah, yes and no. Yes, it has some history information, so looks like momentum. But momentum, remember, was changing your gradient. So momentum, in this case, the gradient is not getting changed, right?
it is getting
Scaled. So that is learning rate is getting scaled. Learning rate is getting scaled based on some history information. But you don't call it momentum because, do you know why it is called momentum, by the way? Because of velocity. So from velocity concept it is coming, that grad of like displacement in velocity and mass times velocity is momentum from that. So that is basically when you are changing. So if you go back, right, in the previous case you will see we were changing, we were adding terms, right? Here we are not adding term. Here the learning rate is getting scaled. Does it have a history information? It is have. Yes, it has. Right? Is that good? Well, right now only I'll prove that, or not prove, I'll just state that it is not always good. Because of this ST term, what it can do is that it can scale it very aggressively. And because it scales very aggressively, the learning rate, I mean the effective learning rate becomes very small, which is probably not a good idea. So yeah, to answer your question, When I say momentum, the gradient terms would be changed. So in that sense, we call it momentum. Momentum does not necessarily means that history being there always is momentum. But yes, so coming to the point, so because st plus 1 is equal to st plus gt, what happens, a problem that happens is that you have too much information of the history. Even if you add a mu is 0.9, even then you have too much information of history. And because of that, this learning rate is modified, scaled quite aggressively, which is not always good. And this is where RMS prop comes into picture.
ST is also a hyperparameter here, but that's not the initialization of that thing.
Generally, we initialize to 0.
0, not Xavier type.
You know, Xavier is not here, right? Xavier is only for parameter. Okay. I mean, you can initially you can set it to be 0. That's fine. So next comes RMS prop, and the motivation is that ADA grad shrinks scales. Scales is probably the correct term. Shrinks, don't write shrinks. I'm deleting it. Just write scales. I mean, shrinks means it is always reducing. Need not be the case, right? Scales theta, not theta. It is learning rate, right? Quite aggressively based on ST. Okay. RMS prop scales eta quite aggressively based on ST plus 1, right? RMS prop addresses this issue. RMS prop addresses this issue. And RMS prop, the story you are aware of. What is the story of RMS prop? So RMS prop was proposed by Jeffrey Hinton, who is a Nobel laureate, one of the 3 godfathers of deep learning. I mean, him along with Benzio and LeCun are called to be the godfather of deep learning and modern machine learning in general. So Jeffrey Hinton is in, I think, University of Toronto. I think he was there. And he was teaching this ADA grad, if I'm not wrong, in the classroom. And that class was being recorded, by the way. And while discussing that this is a problem that we face in ADA grad, it shrinks or scales it quite aggressively. There itself, while teaching in the class, he thought that, okay, but we can always reduce the historical information by bringing a new parameter. And that is how RMS prop was developed. So it was developed while teaching. I mean, he was teaching, and in that process, he developed this RMS prop. Okay, so that's why I find it quite interesting. And here the idea is actually very simple. Only one step changes. So ST, ST no, GT, right? Initially, yeah, GT, sorry. GT gradient is equal to gradient okay, and then the main thing, beta times ST plus 1 minus beta times GT, right? And this solves the problem now. Now you can tune this beta and decide how much information you want from the history and how much importance you want to give to the recent past. Okay, so this will help you with that. And generally beta value is kept at 0.9 or something like that. But keep in mind it is 0.9 times 0.9 times 0.9 times 0.9. That's how it goes. I mean, if you write ST plus 1 in terms of S1, you realize that as because of this, it will 0.9 times t. I mean 0.9 to the power t. So that value will become very small. So it basically gradually shrinks the long-term historical information and only retains the recent past, right? And you can decide this parameter, by the way. And this basically addresses the aggressive scaling that you see in uh, AdaGrad. Okay. And then the last step is as it is, nothing changes, which is theta theta t plus, not plus, minus eta times square root of s t plus 1 plus epsilon times, same thing, I'm just writing the total thing. Okay. So this is your, yeah.
What is the name of this parameter?
Beta is a weighting weighing parameter. I mean, it's a weight, right? You are giving weightage to the history. Okay. Okay. And lastly comes the Adam, which is the one of the most popular algorithms. And Adam is the one that does both, that combines RMS prop with momentum based gradient descent. Okay. Not nest prop, momentum based. I'm not sure why nest prop is not done. Maybe I should try it out. You can try it out. What will happen if you combine nest prop with RMS prop? Maybe that is Adam W. I don't know. I have to check that out. Adam combines RMS prop with based gradient descent, right? It combines RMS prop with momentum based. Nistrop does not. It actually addresses.
It addresses that.
Huh.
So in case of adaptive learning unit,
It already does that.
that will not benefit.
I have to check. I mean, I understand what you're saying. In fact, probably that, yeah, I mean, maybe that is already addressed. Maybe, but yeah, good to check it out, I think. Okay, with momentum based gradient descent. So the update here is as follow. So P t plus 1 beta 1 time pt plus 1 minus beta 1 times gradient L theta t, right? So this is your momentum term. Similarly, you have a st term. So s t plus 1 is equal to beta 2 times st plus 1 minus beta 2 times g, what gt is what I was writing? Yeah, gt. Where gt is same as RMS prop, okay? gt same as RMS prop, okay? Last update is theta t plus 1 is equal to theta t minus eta times square root of s t plus 1 plus epsilon times p t plus 1. Okay. So now you see that both the things are coming into picture together. Um, one is basically the scaling the learning rate. The other one is that bringing the momentum information into your gradient and doing them. I mean, basically it's the best of the both worlds, right? And as I said, Adam was proposed in 2015 or 16, something like that, maybe 14. And there has been newer algorithms that has come up, so you should also read about those. But the matter of the fact is, even today, Adam is the uh, most popular one, at least in conventional deep learning. Physics informed learning, maybe something else is more popular. I mean, something else is definitely more popular. But in general, Adam is still the most popular one, at least, right?
Like not going to digital, because like they are using beta 1 and 1 minus beta 1.
I mean, obviously, that part is obviously there, it is damping out. But somehow I feel that looking ahead is always good, right? I mean, even at least philosophically, I think looking ahead is better. So, at least in that sense, right? Okay. So, this is it for optimization in deep learning. There is one more part I am not covering, but it will be there on the slides. You should read it. So, for Adam, there is something known as bias correction, because all of this discussion we have done based on weights. We did not talk about bias. So, in Adam, there is something known as bias correction. It's 1 slide or 2 slide maximum. Do read about it. The bias correction term, I am not covering that. Okay. But in general, this is all about optimization in deep learning, training, whatever you want to call it, right? So, this concludes our discussion on optimization in deep learning. Now, today and potentially, I mean, potentially 50% of next lecture, we will be talking about things that are not that much mathematical, but it's more intuitive in nature. Okay. So, next thing that we want to talk about is generalization. Now, keep in mind, in machine learning, in deep learning, the objective is not to reduce your loss. I mean, if your loss is going to 0, that might not be the best case scenario. It might be fitting your noise, it might be overfitting. The objective in deep learning is that once the model is trained, it should give good results for unseen input. And that is what generalization talks about, right? Now, why is it that a model will not generalize? Well, there are different reasons, and we'll talk about that now, and we'll talk about that in our next lecture as well, right? So, generalization in deep learning, and it is, I mean, you can write, I mean, nothing will change. It can be generalization in machine learning as well. It is more about generalization is the main thing, because the course is deep learning. I'm writing generalization for in deep learning. Okay. So, the objective in ML and DL is to have a model that performs well on unseen data, unseen input, X star. So, objective is that if it is supervised learning given X star, can I predict Y star with a high level of accuracy. Okay, that is the general objective, right? Well, on unseen data. So this is basically, I mean, you can also think of it is that. So the objective is how well the model generalizes. Okay. So reducing the loss is not the goal. I mean, we want to reduce the loss because we believe that by reducing the loss, we are making our model learn about the training data, which will potentially generalize to new data. Potentially generalize to new data is under quotation, and that is what the objective is. Okay. Now, why do you think a model might not generalize? Can you come up with some reasons why you think that a model, although doing very well on training, need not generalize in case of the testing part? That is one question. And the second question is, how do you test it? But that will come later. So first, let us discuss this. Why do you think a model having low loss during training will not generalize well? Memorization. So that is one point. Let me write it down. So it is not really learning, it is memorizing, right? And not learning. Any other reason?
Maybe the training data is such that always predicting the answer rate works out 90%.
Out of distribution, you mean out of distribution, right? That maybe my training data is biased towards one of the things. So if I look at the class distribution, it changes in the input and output. Out of distribution. Any other reason? I told one reason a little while ago. Overfitting is something I talked about, right? It is learning, but it is only learning to fit the training data. Overfitting. Need not be. Okay. Need not be. Okay. Okay. So let me try and give some examples where this kind of behaviors can happen, right? So suppose we are working with the MNIST dataset. Everyone knows about the MNIST dataset? Is there anyone who does not know about MNIST? Okay. So MNIST dataset is a dataset that has handwritten digits. So 0 to 9, 10 digits. All are handwritten, and because they're handwritten, the writing pattern changes. My handwriting is not same as your handwriting. And someone can write one like this, someone can tilt it, and all of those things, right? So it's a very popular, very useful handwritten digit data set. Okay. So let us think about the MNIST data set. I mean, because yeah. So let's say I have training data and test data in the MNIST data set, right? So 0 to 9 is what I have. And somehow in the training data, this is how it looks. Okay. 9 is like that in one of the training data, right? This is another one. And let's take a third one. Okay. And now one test data, let's say one of the, I mean, there are multiple such, but I'm just showing 3. Okay. This is a test data, let's say, which is also 9, but it's like this. Okay. Now suppose by accident, and it is an accident, okay, this pixel, this pixel and this pixel, these are same pixel locations, okay, these are same pixel locations. So if you consider 29 by 29 grid, let's say it is 13 cross 12, I don't know, I'm just coming up with a number. So same pixel location is the green dots, okay, and that one here is this one. Now ideally as a human you should be able to generalize that if this 3 and 9, the fourth one should also be 9, right? We should be able to generalize that if the first 3 and 9, the fourth one is also 9. But it is possible with this kind of data set that your deep learning model has learned that if the pixel location 13 cross 12 is black, because it is a black and white image, then it should be 9. If that one is white, then it should not be 9. It should be 8 or 7, I don't know. So it is learning, but it is learning some wrong pattern. So it is kind of memorizing the pixel location. That this pixel being black means it's a 9. Now that's not a correct, I mean it's just memorized one pixel and trying to infer based on that. So this is one case where your deep learning model might not work. Although it looks very simple to a human, your deep learning model might give wrong result. What is the solution? In this case, make your data as diverse as possible. Okay. In this case, what? Yes, yes, yes. Yes, but that is one possible solution. But the problem is that you will not know that this is the issue because you will have 60,000 data points, right? So you will not even know. 10,000 and 6,000 is the split. 10,000 training, 6,000 testing is what we use generally for MNIST. So when you are dealing with that kind of data set, you will not even know what the issue is. Or diagnosing the issue itself is a challenge of its own. If you know the issue, we can solve it. I mean, it's very simple. You can just shift it, translation invariance, and all of those things we can bring into picture. It's basically a translation, right? But that we can only do if we know what the issue is, and diagnosing that issue itself is probably the biggest challenge, right?
You can say this thing as a memorization or overfitting because both the things are happening here.
Okay. In this case, overfitting we say generally when the data is noisy. In this case, it is not really noisy. So it is no, it's not noisy. It's clear image, right? What it is doing is it is kind of learning a wrong pattern that was actually not needed. It is learning that there is a pixel. If that one is black, then it should be 9. That's what it is. It has learned, right? Now, so it is actually not learning the correct feature or the correct reasoning. I mean, if I can use the term reasoning, which generally we do not use in case of deep learning, but if we use the term reasoning, then the reason because of which it is classifying something as 9 and not as 9, that reason itself is wrong. So it is learning a wrong pattern in the data.
Very difficult to tell like whether it is memorization or
Obviously. I mean, why it is wrong itself is, that's what I was saying, right? It is anyways very difficult to tell why when something is not working. Because first of all, your data is high dimensional, then your parameter space is high dimensional. And then in this case, you can do it manually, but in most data set, you cannot do it manually also. So there are 3 layers of challenges that are there, and that is there, that's fact. Okay, so yeah. In the training data, pixels, pixel, let's call 12 cross 13, was always black 1. So I mean, black means 1 and white means 0. I mean, that is the notation I'm using. Black in for 9 in training data. Okay. For digit 9 in training data. Right. So the model learned that pixel 12, 13 being black means it is 9, else it is not a 9. Something like this the model has learned, right? And when the model learns something like this, it is learning a wrong pattern in the data, and because of that, it is not generalizing. Okay? It is not learning the correct features that are needed. Let us come back, right? So generally, how do you solve this issue? So generally, the most basic thing to do is that you divide your dataset into training data, validation data, and test data. So you divide your dataset into training, validation, and test. Training data is what you use for training your model. Validation data is what you decide to decide your hyperparameters, and test data is the data based on which you report performance of your model. Okay, so validation data is for hyperparameter tuning, training data is for training, that's the name, and then test data is for reporting performance of your model. Now when you do this, how does it help? Well, the hope is that even if such scenario is there in your training data, the validation data set will have something like the pink one, and then that will be diagnosed at that stage so that your model architecture gets changed and it is able to learn better. That is the hope. Again, many of the things I am going to talk about today and next lecture will be hope only. Okay. So the idea is divide data set into training data, validation data, and test data. Okay. Train data used for training. That's the name. Training means theta update, which means optimization, which means whatever we were discussing till now in the last few lectures was only about this training portion. Right? Validation is for hyperparameter. What are the hyperparameters? Tell me some of the hyperparameters you are aware of. Learning rate, then model architecture, number of hidden layer, number of nodes in hidden layer, the activation function to that you are selecting, and so on and so forth, right? All of those are hyperparameters. So that you decide based on validation data. And test data is for reporting performance. So this one is for reporting performance. And there should not be any data leakage. There should not be any overlap. It should not happen that validation data is common with training data. It should not happen. If that is happening, that is known as data leakage. Data leakage is a crime in deep learning, okay, in machine learning. It's a crime, I call it, okay. So data leakage should not happen. Data leakage is very bad. And then your model is useless actually if there is data leakage. Okay. Now, why do you think a model memorize overfits? Okay. So we talked about overfitting, right? Why do you think a model overfits? Why? Not what? If the model is highly expressive, that can learn anything. So it learns the exact thing, right? So a highly complex model, highly expressive model, complex is probably the wrong term. A more expressive a model, more chances are that it will overfit, right? So overfitting. More complex or expressive is what I said, right? Expressive model is greater the chance it will overfit. Chance it will overfit. So now, if we go by this logic, right, more expressive a model is, greater the chance it will overfit. Then, based on this logic, what do you mean by what is an expressive model? Any idea what an expressive model is? I use the term randomly expressive. What is expressive? When we call a model to be expressive? Hmm? How will you know? If I give you two models, which one is more expressive? How will you know?
If you can prove that anything that the first model says and also written by the second model.
Correct. Correct. How? Give me a very small, easy way of looking into it. You are right.
Larger unit or smaller unit, you can take zero.
Yes, number of parameters, right? More the number of parameters, more expressive the model is. Because you can always make some of these parameters 0 and go back to the original one, right? Which means one way of making your model less expressive is to reduce the number of parameters, right? One way of reducing the number of reducing the expressibility of the model is to reduce the number of parameters, right? And if we can reduce the expressibility to a reasonable amount, I don't want to reduce it too much, then it will not learn anything. So I want to reduce it up to a certain extent. And what is that certain extent is what will be decided during by the validation data set. But if I can reduce the expressibility to a certain degree, certain extent, hopefully the model will be less likely to overfit because the expressibility has reduced, right? So one way is to reduce the expressibility. So one way to address overfitting actually, okay, to address overfitting is to reduce the expressibility, which means reduce the number of parameters, which means this means reduce number of parameters. And here comes the idea of bottleneck layer. So in deep learning, there is a concept of bottleneck layer, which means you add one additional layer, which helps you reduce the number of parameters. Okay, so here comes the idea of bottleneck layer. Okay, suppose I have 100 nodes and then my output is also 100 and then everything is connected. Okay, and this is just two layers I am taking. It might be that there are layers. So there are layers before it, there are layers after it. I'm just selecting, let's say, L minus 1 and Lth layer. Okay, and these are all connected as I said, right? Okay, something like this. How many parameters are there in this layer? Forget bias is equal no bias. How many parameters are there? 100 square, right? Then therefore, right? 100, 100, so 100 square. Number of weights is equal to 100 square, right? Now, let us take the same layer and let us do something else. So this is the L minus 1th layer, and then the Lth layer is there. In between, I add one additional layer. Okay, so the one additional layer I add. Okay, this was 100. This remains to be 100. This is 10. So I added one more layer in between. Now how many parameters? 2000. 100 times 10, 100 times 10. So 1000 plus 1000, 2000. So with this, I mean, I can write cardinality of theta, but let me write like this: number of weights 2 times 1000, 2000. So what happened here? Because I added one additional layer which had less number of neuron, I created a bottleneck, right? Information bottleneck there. And because of that, the number of parameter reduces. As the number of parameter reduces, expressibility reduces. Chances of overfitting reduces. So bottleneck layer helps us in potentially reducing the chances of overfitting. Right? So we'll stop here. Just let me write it down. So bottleneck layer helps reducing the chance of overfitting. Okay, so I'll stop here. This is not yet done. There's also this idea of dropout, and there are other ideas in generalization which we'll talk about in the next lecture. But the idea of generalization in general is that it should generalize to new data. And is there something we can do? For example, yeah, we'll talk about data augmentation and other things in the next lecture. Okay, thank you.